Ever wonder how your computer can sort through thousands or even millions of items in the blink of an eye? From your photo gallery to a massive company database, fast sorting is absolutely crucial. Well, one of the main reasons for this incredible speed is a really elegant algorithm called Quicksort. In this explainer, we're going to break down exactly how it works, but we'll be focusing on the core concepts and the strategy behind its power. And for all you developers watching, don't worry about frantically scribbling down code. I've put a detailed implementation and a line-by-line dry run right in the description for you to explore later. So you ready? Let's dive in. All right, here's our roadmap. First, we'll get right to the heart of what makes Quicksort tick. Then we'll explore its divide and conquer strategy. After that, we'll see it in action with a really clear visual example. We'll break down its performance, the good and the bad, and finally, we'll put it head-to-head with its main rival, MergeSort. So, first things first, what is the big idea behind Quicksort? What's the secret sauce? It all boils down to one simple but really powerful action. You pick an element, any element really, and you call it the pivot. Then you just rearrange the list so that everything smaller than that pivot is on its left and everything larger is on its right. That's it. That's the core magic trick. And what's so critical is that after you do this, that pivot you chose is now locked into its final correct sorted position. This one move is the foundation for the entire algorithm. Okay, so how does that one little trick lead to a fully sorted list? Well, it uses a classic strategy called divide and conquer. Think about it like this. Imagine a librarian with a giant, messy pile of unsorted books. Instead of trying to sort them all at once, they just pick a book with an author's name starting with M. Then they quickly create two smaller piles, one for A through L and another for N through Z. They've just partitioned the problem. Now they can sort those two smaller piles completely independently. And that is exactly what Quicksort does. The algorithm is recursive, which is just a fancy way of saying it applies the same logic over and over again, but to smaller and smaller pieces. So just like our librarian would take that A through L pile and do the same thing again, Quicksort takes those two new lists and runs the exact same pivot and partition logic on each one. It just keeps dividing the problem into smaller and smaller subproblems until the lists are so small they only have one item, which by definition is already sorted. Now this is the engine room of the algorithm. So how does that partitioning actually happen? It's pretty clever. First, as you can see, it picks a pivot. In this particular version, it's just the last element. Then it sets up a pointer to keep track of the boundary for the smaller elements. As it marches through the list, anytime it finds an element smaller than the pivot, it just moves that boundary pointer and swaps the element to the small side. Then, once it's scanned the whole list, it does one final swap to place the pivot itself right at that boundary. And that's how it so efficiently partitions the list in just a single pass. Okay, enough theory. Let's actually see this thing in action. We're going to walk through a quick visual dry run right now to make all of this really concrete. So here's our starting lineup, a simple, unsorted array of 6 numbers. Our mission, should we choose to accept it, is to get this into ascending order. Following the logic we just talked about, we'll pick the last element, the number 5, as our very first pivot. Now let's watch what the algorithm does as it rearranges the list around it. And there it is. After just one partition, notice 2 really important things. First, the number 1, which is smaller than our pivot 5, is now on its left. But second, and this is the big one, our pivot 5 is now in its final sorted position. It will never have to move again. And now we see the divide and conquer part kick in. The algorithm looks at the 2 new subarrays it created. The one on the left, which is just the number 1, well, it's already sorted. But that subarray on the right, the 8, 9, 10, 7, is still a mess. So what does the algorithm do? You guessed it, it runs the exact same process again. It's going to pick a new pivot, 7 from this list, and partition it all over again. And this process just keeps going, partitioning, making new subarrays, and partitioning them again, until every single subarray is sorted. And when all those recursive calls are done, we're left with this, the final, beautifully sorted array. From chaos to order, one pivot at a time. Okay, so we know how it works, but the real question is, how well does it work? Let's talk about performance, because this is where Quicksort really shines. Well, most of the time. On average, Quicksort is incredibly fast. In computer science terms, it runs in O of n log n time. That's just a very efficient way to say that as your list gets bigger, the time it takes to sort grows very, very reasonably. This happens when our pivot does a good job and consistently splits the array into two roughly equal pieces. But it has an Achilles heel. If you get really unlucky and always pick the smallest or largest element as your pivot, you get a totally unbalanced split, and the performance craters to O of n squared, which means the sorting time can absolutely explode for large data sets. Now, let's talk about memory. Quicksort's space complexity is excellent at just O log n. Because it sorts the array in place, meaning it just shuffles elements around without making whole new copies, it uses a very, very small amount of extra memory, mostly just to keep track of all those recursive calls. So let's just quickly summarize its key advantages. In the real world, it is often faster than its main rivals because it has lower overhead. And that in-place sorting is a huge win. It makes it incredibly memory efficient, which is so critical when you're sorting massive data sets. But hey, no algorithm is perfect. That worst-case O of n squared performance, while it is rare, is like a potential landmine you have to be aware of. It's also what's known as not stable. This is a key point. It means if you have duplicate elements, say 2 7s in your list, Quicksort does not guarantee they'll stay in their original relative order. Now for sorting simple numbers, who cares, right? But what if you were sorting a customer list by last name? You'd probably want the first names to stay alphabetized. Quicksort might shuffle them around, and for some applications, that's a total deal breaker. And that brings us to the final showdown. You can't really talk about Quicksort without comparing it to its main rival in the ON log n sorting club, MergeSort. Looking at this table, the trade-offs become crystal clear. Think of MergeSort as Mr. Consistent. Its performance is always a solid O n log n, and it's stable. But that consistency comes at a cost. It needs extra memory, O n space, to do its job. Quicksort, on the other hand, is the speed demon. It's generally faster in practice and incredibly space efficient, but you're kind of gambling on avoiding that nasty worst-case scenario, and you have to give up stability. So if there's one thing to take away, it's this. Quicksort is a brilliant piece of engineering. It's elegant, it's powerful, and it's usually blazing fast, which is why it's so widely used. Its brilliance, however, is directly tied to its one major vulnerability, the choice of the pivot. And that really leaves us with a final thought to chew on. In a world that so often demands both reliability and performance, choosing between an algorithm like Quicksort and one like MergeSort isn't just a technical decision, it's a strategic one. It forces you to ask, when is a guarantee of consistency more important than a shot at pure speed?